Hey guys, this lesson is 9.2 for Calculus BC, and we're going to start to introduce, we had talked about what a sequence is. Now we're going to talk about what a series is, and throughout Chapter 9, you're going to be learning several series tests. We're also going to start to see the first two in this lesson, which is the geometric series and the nth term test. So a series, in respect to what we had learned of a sequence, if a sequence was writing out those list of terms, a series is just taking those terms and adding them up together. So you might see it be called, if a sub n, which we learned last class, is that infinite sequence, then this notation right here, this fancy letter E, is a Greek symbol for summation. Okay, it's called sigma. So summation, we know, means to add. So you're just going to take all of the numbers in the sequence and add them up. Now, this number in the bottom tells you which term to start at. We're starting at the first term, right? And this case is to go to the infinite term and add them all up. Okay, this top number, if you've taken a previous maybe algebra or trigonometry class, you might have seen that maybe is the 5, let's say. So n1 to 5 just means you're going from the first to the fifth term and adding them up. Okay, so this can be called an infinite series when there's an infinity there, but if they just put the word series, that also denotes the infinite one. Okay, and then if they do not put the little n equals 1 or the infinity, we can assume that that means the infinite series. It's so commonly used that they don't have to put it. Okay, so to begin with, we can start by doing what's called a partial sum. It's kind of like a slow estimation process for the actual summation. So what it looks like is we'll first find the sum of the first term and then the sum of the second, right? So that means we add the first term and the second term. If we say s sub 3, that means we're only adding the first 3, and so on and so forth, okay? Partial sums is used to be able to test if the series is going to converge or diverge. So here it states that if the partial sum converges or diverges, we can assume that the series will also converge or diverge. So the way we're going to test this out, we're going to take a few steps. First, we're going to write out the first few terms of the sequence, okay? Then we're going to try a few partial sums like it shows here. Once we come up with a few partial sums that we start to analyze what's happening, we can create a function like we did at the end of last lesson. Using that function, we can test it with a limit as n approaches infinity, and if that converges or diverges, we can determine whether the entire series converges or diverges. So let's take a look at what these steps look like in a problem, okay? So it says solve the series, and we're going to use partial sum. So step 1 is going to be to write out a few terms. So this summation would be saying 1 over 2 to the first, which is 2. Then we have 1 over 2 to the second, which is 1 over 4. Then 1 over 2 to the third, which is going to be 1 over 8. And then 1 over 2 to the fourth, which is 1 over 16. And so on and so on and so on, right? So we wrote out a few terms. My next step is going to be to try out partial sums. So S sub 1 means just adding the first term with itself. So I just have 1 over 2. My second one is going to be that 1 over 2 plus the first two terms, right? 1 over 4. Okay? If I get a common denominator, I have 2 over 4 plus 1 over 4, which gives me 3 over 4. Okay? Let's go to the third. I'm adding the first 3 terms together. Now, if we just added on the previous step 1/2 and 1/4 and got 3 over 4, I'm really just adding that 3 over 4 to the 1 over 8. Now, if I need a common denominator, 3 over 4 plus 1 over 8, this would become 6 over 8. And that would give me 7 over 8. Okay? So analyze. Now, our next step is going to be to come up with a function. So if my first partial sum was 1/2, and then 3/4, and then 7/8. I like to analyze my denominators first, okay? I know that when I add up 1/2 plus 1/4 plus 1/8 plus 1/16, and then I keep going, plus, remember, my last term is 1/2 to the n. My denominators went from 2, 4, 8, and we can see that because we multiplied this. First we had 2, then we did 2 times 2, which is 4. Then we did that 4 times another 2, which gave me 8. And then times another 2, which is 16. So I have 2 constantly being multiplied by another 2. So I have 2 to the nth power, right? We see just like the original pattern, 2, 4, 8, 16, 2, 4, 8, and we'd keep on going. Now my numerator, if you catch, is always 1 less than my denominator. So I can write 2 to the n, whatever I got for my denominator, minus 1. And there is me creating a function. My next step is going to be to test the limit as n approaches infinity. Now, if I plug in infinity, I have 2 to the infinity minus 1 over 2 to the infinity. Anything raised to the infinity, it's going to give you infinity. So I can use L'Hopital's here. So the derivative, this is an exponential function, a to the u, if you've seen my other videos, is to rewrite times ln of the base, and then times the derivative of the exponent. Derivative of a variable is just 1. And then minus 1, derivative of 1 is 0. Okay, and then in the denominator, I'm going to have the same thing. And notice that all of this cancels out and reduces. So I'm really working with the limit as n approaches infinity of 1, which equals 1. And since I have a number, I can say that it converges. And we just stated in our notes that if the limit of the partial sum converges, we can also say that the series also converges, right? The sum of all the numbers will also converge. All right, let's check out another one. The given is the infinite series of 1 over n minus 1 over n plus 1. So step 1, let's write out a few of those terms. If n is 1, then I have 1 over 1 minus 1 more than n, so 2. My next one, my second term, would be 1 over 2 minus 1 over 1 more than 2. My third term is going to be 1 over 3 minus 1 over 1 more than 3. And let's do one more. My fourth term will be 1 over 4 minus 1 over 1 more than 4, which is 5. And then obviously this continues on and on and on and on. Now, I know last time I put plus signs to represent the series. Here I put commas to represent the sequence. As long as you just know what's coming next, it doesn't matter which way you write it. This is all a step to find your partial sum, okay? I'm going to show you 2 different ways to do this. The first one is a little lengthy, so I'm going to encourage you to have your calculator out for adding and subtracting these fractions. And then the second is more of a shortcut where you'll find very useful if you're in the AP test and you see that you're not allowed to use a calculator, okay? So let's start off with a step of doing the partial sums. Okay, so if I'm just adding the first term or including the first term, this is 1 minus 1/2, which gives me half. Okay, the sum of the first 2 terms is going to be half And then I'm going to add 1/2 minus 1/3 in your calculator is 1/6, okay? Now, if I get a common denominator here and I add this together, I'm going to get 2/3, okay? The sum of the first 3 terms, I had 1/2 plus 1/6 plus 1/3 minus 1/4 is going to give me 1/12. Add that up with a common denominator, put in your calculator, and you should get 3/4. And that's being reduced, obviously, right? I'm going to do one more term. So the sum of the first 4 terms, I had 1/2 plus 1/6 plus 1/12. And then if you combine in your calculator 1/4 minus 1/5, you get 1/20. Okay, put that in your calculator and you should get 4/5. Okay, so this is the lengthy version, the one you'd probably need your calculator for. If you catch, okay, that, I'm going to put it in a different color. When you add this up, so if I start to add all of these, you'll notice I have a -1/2 and a +1/2. That's going to cancel. And then I have a -1/3 and a +1/3. That's going to cancel. A -1/4 and a +1/4, and that'll cancel. And that'll keep happening. So, for example, if I'm doing to the 4th term, right, I'm including all of these, and the only ones that don't cancel is the first and the last, okay? If I'm doing to the 2nd, only this one and this one, right, then I don't have anything to cancel this -1/3, so I'm really only combining this first and this last. And for this term, it would have been the first and the last because there would have been nothing for this -1/4 to cancel with, okay? So it is also safe to say, right, here's the shortcut version if you don't have a calculator. This is obviously 1/2. But when we combine the first 2, I would have had 1. The 1/2 would have canceled, and I would have been left with a -1/3. And maybe that's easier to do as opposed to, you know, using your calculator. If you don't have one, you could do this one by hand. And the 3rd, right, would have been, so here's the first term, the 2nd, and the 3rd. I would have had nothing to cancel this. -1/4, so I had 1 minus 1/4. So here we have 1/2. Here we're going to have 2/3. Here we're going to have 3/4. And same thing for the 4th term, right? It would have been 1 minus, nothing to cancel this one out with. Now we're including this term. And I get 4/5. Okay, so with calculator, without calculator, you have 2 options. Now let's come up with the nth term, okay? Sorry, the sum of the nth term. So sum of the nth, I'm noticing that for my first term, I have 1/2. Second term, 2/3. Third term, 3/4. Fourth term, 4/5. So notice, depending on what term I'm adding up to, that is going to be the same as my numerator. So 1 and 1, 2 and 2. So I can say that I have here n over, and notice that my denominator was always 1 more than the numerator, okay? Next step is going to be to find the limit as n approaches infinity. Now, if you plug in your infinities, you're going to get infinity over infinity. So then you can use L'Hopital's. You could have used the horizontal asymptote rule there. But if I do L'Hopital's, then I have the limit as n approaches infinity. Derivative of n is 1. Over derivative of n is 1. Derivative of 1 is 0. So I get 1. Which means if I get an actual number, that means this converges. And according to partial sums, we said that if the limit of the infinite summation converges, then we can say that the whole series converges. All right, and then down here, it's just the fancy notation you're going to see in the textbook of what we just talked about, that they give this process whenever all of these start canceling. They call this a telescope series, okay? So basically it means you'll be left with the first and the last, depending up to what number you go up to, okay? And then the nth partial sum will be the first term, right? We said the first minus b sub n plus 1. So if we want to add the first 3, right, when we did 3, 1, 2, 3, we were left with that negative 1 over 4. So if it was a third term, 3 plus 1 is 4, and that's why we used the fourth one, right? And then if the series converges, its sum, right, will be the first term minus the limit as n approaches infinity of the last one, which was what we talked about here, okay? For this next example, it's just an example where maybe you don't have to do that much work or overthink it, okay? Start to try to understand the concept of just adding these numbers together. If I want to know the infinite series of 1, that means my function is 1. That means my first term is going to be 1. My second term is also going to be 1. My third term also 1, and so on after that, okay? If my function is just a constant, no matter which term I go to, I'll just still have that constant. And as I add those up, so if I add 1 up an infinite amount of times, I'm going to end up with infinity. Okay, I didn't have to do a partial sum here. There weren't any crazy fractions to look at. And the moment an infinite series equals infinity, right, we know that this diverges. And we're done. Okay, so they're not all as complicated. Sit and analyze it before you start working, okay? So partial sums is this way of taking, step by step and actually adding those numbers and seeing what's going to happen. Just like when we learned limits and then we started to learn derivative, the limit version, and it was really lengthy. And then we started to learn all these shortcut formulas for derivatives. Same thing in integration. We're going to now learn all of these shortcut formulas so that we don't have to do this lengthy partial sum every single time. Okay. The first test you're going to learn, it's called a geometric series. So if this series has this pattern of what they call geometric, you can take this super quick shortcut. The setup that you're going to be looking for to know and recognize that it is geometric, it is a times r raised to the n. Now, a and r will both be numbers, okay? N is going to be your variable, and you know that because there's an n down here. This will always denote your variable. So notice that the entire r is raised to n, to your variable. A serves more like a coefficient, okay? So if the absolute value of r is greater than or equal to 1, you can conclude that this diverges. If the absolute value of r is less than 1, then it is going to converge, and I can even find out what number it converges to by saying a divided by 1 minus r. Okay? I think the only thing that can get a little tricky here is maybe having to rewrite this so that it does look like this. Again, that entire r needs to be raised to n, okay? Anything else, I would pull to the front as the coefficient a. So some properties to remember is that coefficient can be pulled to the front just like you've worked with in derivatives and integrals and deal with it at the end. So if c here is my coefficient, I could take it out and multiply it to the answer of my summation of just this a sub n. Same thing if they're being separated by addition or subtraction, I can solve each of them and then add their answers. And then these properties over here are back from algebra. And that's remembering that if I have an exponent to two things being divided, that exponent really belongs to both. And this works both ways, okay? So if I have something that looks like this, I can say that r is just a over b, right? Because the whole thing is really being raised to n. Remember that 1 raised to any exponent is just 1. So if I only see the exponent on the denominator, but my numerator is a 1, I can rewrite it this way, and now I can spot my entire r. All right? So let's take a look at these examples. The first one says to solve the infinite series of 3 over 2 to the n. Now, you always want to ask yourself, mind you, here it says it's geometric, but when you're looking like at an AP test or a chapter test, they're all mixed. You don't know which test we're using. So I want to see if I can get an r, something in its entirety, raised to n. And if I need to, I can move something out as a coefficient. So what I might want to do is rewrite this 3 up in the front, and I can say this is the infinite series of 3 times 1 over 2 to the n, right? We agree this is equivalent. Now, I still don't have an entire thing raised to the n, but just like we talked about over here, if the n is just to the denominator, but the numerators are 1, I can rewrite this, okay? And as you get good at these, you'll do this a lot faster. I'm just taking it step by step. And now I can clearly see that this right here is my A, and this right here is my R, okay? So now, because R, which is 1/2, or we'll even say the absolute value of R, which is 1/2, since this is a number less than 1, I know that this converges, right? Not only can I determine that it converges, but based on the geometric series, I can even find out what it converges to. And that would be A, which is 3, over 1 minus R, which is 1/2. So that's going to be 3 over 1 minus 1/2 is 1/2. I'm going to change flip. If you feel the need to rewrite 3 divided by 1/2, so you see it a little better, this is going to be 3 times 2 over 1, which is going to give me 6. So this series will converge, and when you add up all those numbers, it converges to the number 6, okay? Let's take a look at this next one. I have the infinite series of 3 over 2 raised to n. Now, here from the beginning, I see an entire thing raised to n, to my variable. So I can already claim this to be my R. And you might think, hey, my A is missing. But remember, this is multiplication, so my A is being multiplied there. We could say that A is 1, okay? So if R, absolute value of R, is 3 over 2, this is a number that is greater than 1, okay? So this diverges. And I'm done. All right, our second test for this lesson is called the nth term test for divergence. So that means that this test can only be used to prove divergence, okay? I'm going to tell you right now, this is the first test you want to try. It is the easiest, the quickest, and it eliminates you spending time trying to identify, okay, which test do I use? You can always use this one first, okay? And all it says is that if you do the limit to infinity and you get anything other than 0, it diverges. If you get 0 as your answer, you cannot say that it converges. It just means you have no conclusion and you're ready to move on to look through your other tests, okay? So let's check this one out. First example, the infinite sum of 2 to the nth power. I'm going to try the limit as n approaches infinity of 2 to the nth power. Well, 2 raised to infinity, if I have infinity in the exponent, this equals infinity. Infinity is not 0, therefore, this diverges. And we're done. This is a quick, easy test to try. Okay? Just so you get a visual understanding, 2 to the nth power is like saying e to the n, like e to the x. It's an exponential function. So if we're thinking about all the numbers from 0, right? All of what these y values would be, they continue to get bigger, and if we add them, it should make sense that as we add bigger numbers, it is going to go to infinity, okay, which means that it diverges. Let's look at the next 2, okay? I'm going to try the limit as n approaches infinity of n factorial over 2n factorial plus 1. Now, I know this feels lengthy to rewrite all this. If you're in a multiple choice, I get it. But please remember that if you are solving a free response question on the AP test, every step of your notation counts towards your points. So please make sure you write this out, okay? So I have infinity factorial, which equals infinity, over 2 times infinity factorial plus 1, also infinity, which means I can use L'Hopital's. Again, all of this would count towards your point, stating that you have to use L'Hopital's. So if I obviously don't know a derivative rule for n factorial, but if I use the horizontal asymptote rule, I know that my coefficients, being that, remember, horizontal asymptote rule, I don't have to worry about this. Being that I have n factorial and n factorial, I'm really just looking at these coefficients. So that means that my answer to this is really just going to be 1/2. Since 1/2 does not equal 0, right? Does not equal 0, if you want to write it, I can say that this diverges. All right, and let's look at this last one. First test I'm going to try is the nth term test. Try the limit as n approaches infinity of 1 over n, and I get 1 over infinity. This is a bottom-heavy fraction. Bottom-heavy fractions equals 0. Now, according to my rules, if this equals 0, I cannot say that it converges, right? I could just say that I have no conclusion. And then once I learn the rest of this chapter, I would try another test. Okay, so if we were to seeing this question on an AP exam, I wouldn't just write no conclusion as my answer. I'd actually try one of these upcoming tests that you're going to learn until you do have a conclusion of convergence or divergence.